As geoscience disciplines increasingly integrate artificial intelligence to enhance data analysis and decision-making processes, AI algorithms are being employed to not only process large amounts of high-resolution data quickly, but AI-driven predictive modelling is being employed to assess the likelihood of finding resources in underexplored regions like those under significant cover. The use of AI in geoscience has the capacity to revolutionise our understanding of the Earth's systems. Our second keynote is by Nicole Roocke, Chief Executive Officer of the Minerals Research Institute of Western Australia, and she is talking to us today about a future with artificial intelligence, including some collaborative work between Merriwa and GSWA.
So artificial intelligence has been a concept that's been around for over 50 years now. However, it gained significant momentum in the last 2 years when in November 2022, a company called OpenAI released ChatGPT. It had 1 million users in its first week and 100 million by the end of the second month. In January 2024 alone, the website attracted 1.6 billion users. I don't know about you, but my initial reaction to ChatGPT was one of hesitation, resistance, suspicion, concern at the unknown about what happened in the black box, and didn't really want to have anything to do with it. But I have to admit, that's not such a great reaction for a CEO of a research organisation that seeks to push the boundaries of science, innovation and technology development. I was fortunate at that time to be having a discussion with Melinda Hodkiewicz, who challenged me to be able to think about how could we possibly use AI tools to be able to run queries on the reports that MRIWA has collected over the last 30 years of us providing financial assistance. We discussed how we could gain insights that would otherwise not known by having our reports on a static SharePoint site and just using basic search functions. So that started my journey with a future with AI in it. And I'm speaking to you today not as an expert on AI, but someone who's really struggled to get my head around it, around what it is, what are some of the challenges for its use in a technical domain, and what needs to happen to be able to enable the emerging opportunities. So our journey started with a group of third-year computer science students at UWA working on a project to develop a tool which we could use to be able to run text-based queries on our reports. This was then followed up with a subsequent seed project, again at UWA, where we sought to progress the development of that tool and address some of the challenges that we identified in the first project. And boy, has it been a real learning experience for me. For something that's meant to deliver information in natural language, that's something that's easy to understand, AI has a language all of its own, just like the geoscience domain. And while I'll never understand the code or the algorithms or the black box that makes AI works, and to be honest, I don't actually need to, I was in a meeting the other day where there were people discussing a potential AI project, and they were really grappling with what the differences were with the terms and what the implications were for that on the specific project. So it struck me that it was useful to share what I've learnt from the two projects that we've done, the importance of having a level of awareness of what these terms mean, to then be able to understand what the potential challenges, risks and opportunities are from proceeding down a path where we're looking at greater utilisation of AI tools. So here's my attempt to give you a crash course in the terminology and why it's important, and my apologies to those in the room who I know a lot more than me in this space. So let's start with what AI is. Well, it refers to the ability of machines to be able to perform tasks that typically require human intelligence and produce human-like text and dialogue. It has the potential to gather vast repositories of geological, geochemical and geophysical data and reports, and to use it to improve the odds of success by spotting new patterns that don't fit known models or systems. Generative AI, or Gen AI, is a specific type of AI that can create new content. This could be text, images, music, even videos, and I did have a play with having my own little avatar deliver this speech for you, or at least the introduction, but that was just all a bit too freaky. So generative AI certainly moves beyond using data in a tabular format. So what I'm going to focus on is not using AI tools on raw data or data in a tabular format, but rather on its use on reports and providing text-based answers to queries to enhance decision making and to give us an edge to surface new information and options that we would otherwise not have. What's important to know here is that when using AI tools like ChatGPT, is they don't actually know if the answer that they're giving you is right or wrong. It's merely predicting what the most likely sequence of words are based on the query that you've given it and the material that it's been trained on. Tools like ChatGPT use large language models. These models are trained, and yes, I'll get to talking to training, how you train an AI tool in a moment, on huge amounts of text to generate human-like responses to all sorts of prompts and questions. They don't memorise facts, they don't learn in the same way we do, but they learn how words, sentences and ideas are connected, and that allows the AI tool to generate text in a conversational way. This can make them subject to what's called hallucination. That is, being able to generate answers that are inaccurate or worse, completely fabricated, but actually sound good. If you don't have domain-specific knowledge on the topic to actually know any difference. So as described by Amazon Web Services, you can think of large language models as an over-enthusiastic new employee who refuses to stay informed with current events, but will always try to answer every question with absolute confidence. So how do you train an AI tool? Well, they're trained on information that's publicly available on the internet. They're trained on information that third parties provide access to, or that users or human trainers actually provide or generate. In their development stage, the models read large volumes of text and it learns to predict the next word in a sentence based on the text data that's being used. It's then fine-tuned where humans provide feedback in the initial stages, and then the model learns to prefer the types of answers that humans rate highly and to avoid less helpful answers. How's that feedback provided, you might wonder? Well, for a long time, every single time you were asked to prove that you were not a robot by selecting all of the squares that have a traffic light in it, for instance, or you were helping to train an IA tool, firstly in poorly scanned text and then in images. But even if you throw all kinds of feedback and text at a model, it's not going to magically know everything. These tools only know what it's been taught. There's still a need to annotate text to be able to help the tool know what it is looking at, and I'll talk to you about this soon. But tools like ChatGPT have been trained on text contained on the internet. This raises real challenges when you want to use it in a domain-specific area like geoscience disciplines. The AI models need frameworks to be able to categorise and organise information. There are different ways this can be done, and depending on the approach used by an AI tool will actually influence how it predicts what the next word is in a sentence. So let's take a look at some of the different ways information can be categorised and organised to help consider the impact of these when using them in domain-specific areas. I've tried to find visual examples of what the different terms mean to be able to help assist you understand the difference between them, because it did take me a while. So we'll start with vocabularies and taxonomies. Vocabularies are mere collections of terms and phrases within a specific domain. And GSWA subject matter experts have been creating standardised and well-defined geoscientific vocabularies as a crucial first step in ensuring that the data can be effectively shared and utilised, that there's some common language. And I encourage you to seek these out and take a look at them. But taxonomies go a step further. They provide a hierarchy structure that you can then categorise information. So picture a family tree at the top and you have a broad category, and as you go down, you find more specific subcategories, or sideways as the case is on the one on the screen. There's then ontologies and knowledge graphs. Ontologies take taxonomies a step further by defining the relationships between the different concepts. They provide a more complex structure that explains not just what things are, but how they relate to one another, as can be seen by the example on the screen. And then there's knowledge graphs. These are like a web of information, which is a way to visualise the information resulting from ontologies. They connect various pieces of data through relationships, helping machines to be able to understand the context of those terms. You often see very simplified forms of knowledge graphs. However, as you can see from the image of the screen, they can be very complex. This one involves many entities and crosses multiple domain-specific areas. It was generated as part of one of our projects and shows MRI-WA in relation to all of the other data points in our reports. Pleasing for me, it positions MRI-WA at the centre of the universe, it seems, but not surprisingly, since our name was in every single one of those reports. And lastly, we have schemas. Schemas define how data is structured and how different elements connect. For example, a schema for our report database might specify that each report has a title, an author, and a publication year, creating a clear framework for managing that information. While I've tried to really simplify things, hopefully you'll see by the end of the presentation why having an understanding of how information is organised for use in AI is important when you're looking at using different AI tools. I mentioned at the outset we've done a number of projects in the last 18 months to start us on a journey of using AI. Acknowledging my suspicion and concern at the use of such tools, I wanted this done in a relatively low-risk environment, and of course, that was also at low cost. I just want to call out Melinda Hodkiewicz, Caitlin Woods and Henry Scafidi for encouraging us to go down this journey and also supporting me along the way. So the challenge I set for the first project team was to find a way to create a tool, a chatbot, as can be seen on the screen, through which we could run text-based queries on our reports with the following constraints. None of our reports could be uploaded into the open internet. The answers to the queries must be from our report, so it had to be contained. And then we also wanted to be able to provide a reference to which report informed the answer, so that we then had a mechanism to be able to check the accuracy of the answers and acknowledge the original source of where the information came from. This doesn't happen in tools like ChatGPT. At the moment, this tool is only being used internally as we work through some of the issues that I'll cover today. Given the constraints I mentioned, it led the team to using an approach called Retrieval Augmented Generation, or RAG for short, just some more jargon for you to get across. So RAG's a hybrid approach. It's a system that's used to be able to fetch information from a knowledge base, in this case, our reports, the database that holds our reports, and then provides that information to a large language model that then refines or expands upon this retrieved information to be able to produce a more contextually appropriate and fluent response. By using this approach, it ensures the AI tool has access to accurate and relevant data and should help minimise the risk of the model generating incorrect or nonsensical information. Stop it from hallucinating, like I just talked about. It can also show you which documents were used and how they influenced the final output. This level of transparency is crucial for building trust and accountability in the system, particularly when used in a professional context for decision-making purposes. But the system still needs to be trained on domain-specific terminology and concepts. Across the industry globally, despite there being a lot of work going on to create vocabularies, taxonomies, ontologies and knowledge graphs all relating to geoscience, there's actually no agreed approach and much duplication of effort starting to emerge. I've touched on the work happening at GSWA on the development of their vocabularies. But there's further work that's needed to turn these into comprehensive knowledge graphs, specifically for the geoscience domain area. In our second project, Henry Scafidi completed his honours investigating the use of RAG on our technical reports, using a tool called GraphRag. This wasn't the original intention of the project, but things are moving quickly in the Gen AI space, and you need to be prepared to pivot if you enter into these kind of projects. So when this tool was released, we saw opportunity for us to be able to expedite some of the work we were doing and investigate its potential to extract a knowledge graph out of raw text from our reports. But to do this, you still need to define how the data define how data is structured and how those different elements connect. And you can see here how Henry, Melinda and Caitlin have applied, we've had to use humans to be able to train the model on how these schemas apply to our reports. They used the schema that I showed earlier to be able to annotate parts of the text in our report so the machine knew what different terms were, like Big Bill. Even at this point, depending on your area of subject matter expertise or perspective, you can get variability in how how things are annotated. And then, even after the system was trained on the schemas, what Henry discovered was that depending on how you define the schema in the first place, impacts on the accuracy of the answers that were provided. And again, it needs to be humans that provide those initial assessments and provide that feedback to the model. And here you can see how responses generated by asking exactly the same question on exactly the same set of reports but using different schemas provide different quality of results, with green being the most correct and red being the least correct. To continue our journey, in partnership with GSWA and their colleagues from South Australia, we're involved in a further project led by the University of Western Australia called ChatGeo, which seeks to go beyond our existing project and encompass not only text, but also charts, tables, and maps within the many technical documents held by these three entities. Further, we're in the process of initiating work through the ARC Centre in Critical Resources for the Future, which was launched yesterday, is the creation of a data portal or platform for all the projects at the centre to further extend the work of ChatGeo and to maximise the value of that data generated across the entire work in the centre. And at MINEC CRC, which both GSWA and ourselves are participants in, they're seeking to develop and demonstrate and test a mineral systems-based workflow, including standardised ontology, integration of legacy data and acquisition and interpretation of new data sets to be able to determine the potential for mineralised terrains undercover. They're working to apply these newly established vocabulary and produce knowledge graphs representing scientific knowledge from the various case study areas. So my reflections on the journey that I've been trying to get my head around what a future with AI looks like. It has enormous potential, and it's now widely adopted by the general public through things like ChatGPT and the chatbots you engage with on almost every website that you go to nowadays. Most people probably don't have any idea the degree to which they're engaging with various AI tools. It does have a long way to go in domain-specific areas such as the geosciences, and even further once you start looking at integrating use of it along the entire mining value chain. But there's a significant amount of work underway, and I've only touched on a small number of projects we're directly involved with or are being progressed by our research partners. Given the multiple projects around, there's emerging duplication of effort and there's opportunity for further collaboration with subject matter experts across the research community, industry and government to ensure the comprehensive development of systems and protocols for how we classify and organise information within the domain of geoscience. Supporting the ongoing development of open source information like GSWA's vocabularies will become increasingly important. I know both the team at MRIWA and GSWA would love to continue the discussion with you all on the opportunity for further development of ways to organise the information on the creation of generative AI tools to assist with knowledge creation and how we can collectively train them. So you may be wondering why I tried to give you a crash course in the language of AI. AI is not going to be a replacement for traditional geological expertise. While it can produce responses that seem coherent and relevant, as mentioned, it lacks true comprehension. AI models don't understand context and meaning in the way that humans do. They recognise patterns in data and generate outputs based on those patterns. It does have the opportunity, however, to enhance your expertise. If you haven't done so already, as you commence your journey on using AI, as you consider using various tools and systems that are now being developed by a multitude of parties, it's fundamentally important for you to understand the way information has been categorised and organised, as this will significantly influence the pattern it recognises, the types of queries you can run, and the accuracy of those queries. It's also important for you to understand the inherent data sets the systems are trained on, as this will also significantly influence the patterns it recognises, such as putting Meroa at the centre of the universe. So in summary, while AI holds tremendous promise for enhancing our work in geosciences, we must also be really aware of the challenges that it presents. From data quality and hallucination to the lack of genuine understanding, these issues highlight the need for careful implementation and oversight. But most importantly, there's a need for us to be training these systems in exactly the same way that we would invest in training that new employee who's enthusiastically ready to tackle any of those questions. Thank you.